Good evening, everyone. We are in the week 4 problem solving session of the NPTEL course, Basic Electrical Circuits, and week 4 is about nodal analysis. Let me share my screen. So, in the past week, we have discussed about power and energy in circuit element, and towards the end, we have also discussed in order to solve a circuit, how many equations we are supposed to get, and what equations we'll be getting. So, we'll start from this point, and let me just consider this point. So today is week 4, but I'll just start with this. So if we discuss about the circuit analysis, which we have discussed in the last week, we have circuit analysis. So we have discussed if there exists a circuit with n nodes and b branches, with n nodes and b branches, then we have realized that it will have we need to get 2b independent equations because we need b voltages and b currents. So for each branch we need one voltage and one current we have to find out. So we have to find b voltages as well as b currents. So we need to get overall 2b independent equations, and how we'll be getting, we'll apply KCL at every node, KVL in every loop, and IV characteristics in every branch. So we'll be getting n minus 1 KCL equations, because if there are n nodes, we'll get n minus 1. And we have also discussed how we'll be getting KVL equations b minus n plus 1 or b minus n minus 1, or IV characteristics as b. So that we have discussed in the last week. But today we'll be discussing about the nodal analysis. And when we say nodal analysis, it is all about the KCL. So we'll be discussing about how to write the KCL equations in a given circuit. So a circuit can have resistors, a circuit can have voltage sources, a circuit can have current sources, a circuit can have dependent sources like current control current source, voltage control current source, voltage control voltage source, current control voltage source. We have discussed four such dependent sources exist. So for a given circuit, how we can directly write the KCL equation so that we can solve a given circuit, or how to save time in writing these equations, because if the circuit gets complicated, then the number of equations or the number of nodes at which we have to apply KCL will also increase. So how are we going to save time, or is there any shortcut for that? That we are going to discuss. So initially we'll do in this way. There are like, first we'll discuss about the theory, we'll solve a problem. Then there are some corner cases where you cannot directly apply the theory that we have learned, but you have to somehow apply that theory and do some basic modifications, and then you have to get the equations. So first we'll discuss the theory and then we'll solve the problem subsequently, instead of learning the theory at a time and solving the problems at a time, which we had done in the earlier weeks. But this week I'm going to do in a different way, so that it will be easy for you to understand. Yeah, Gayatri, good evening. I hope I'm audible. So yeah, this week we'll be discussing about nodal analysis, and we just now we have started. Yeah. So first, we'll discuss with the easiest circuit. So for applying the nodal analysis, the easiest circuit will be consisting of a resistor and current sources. I will be considering the same set of circuit that sir has considered. So it will be easy for you to look back into this video and understand the concept that sir has explained. If I explain a different circuit, then you will be looking at two different circuits. So that's why I'll keep it common and I'll just explain the circuit that sir had already explained. So if you have or had any doubts at that time, you can ask me, and that concept will be much more clear. So first we'll start with the circuit with resistor and current sources. So the basic aim of today's session is to make sure that you people will understand how to apply nodal analysis for any circuit. First, we'll start with the easiest circuit and we'll slowly add some difficulties and we'll see how we are going to address them. So let me draw the circuit that Sir had considered in his lectures. So this is the circuit that Sir had considered earlier. So let me use red color. These are called as I1, I3, R11, R12, R13, R12, and R23. And I'm sorry, this sir has considered as R22 and R23. So let us follow the same convention. So how many nodes we have here? We have four nodes, which are this is node 1, this is node 2, and this is node 3, and this is node 4. So if there are four nodes, then we will get how many? N minus 1 KCL equations. So we will get three KCL equations, which means we'll apply KCL at three nodes. So other node we can consider it as ground. So that's what I have done here. So I have considered it as a ground. So now if we start, the current direction here is like this. So in the nodal analysis, the convention that we have to do is we have to consider the currents are flowing away from the node. So this is flowing away, this is also flowing away, here also flowing away, here also flowing away, and here also flowing away. So that is what the convention that you have to consider. Consider that the currents in the branches are flowing away from the nodes. Okay. Now we'll apply KCL at each of these equations. So we'll write it in this form that I'll show you how. So first we'll apply KCL at node 1. So current entering equals to current leaving, right? So first I'll write current leaving, then I'll write current entering. So let this node voltage be V1, this be V2, and this be V3. So are you following? Hello, whoever has attended is attending, sorry. Are you following whatever I'm saying?
Yes, sir.
Okay. So now current leaving is this current plus this current summation, right? So I'll write V1 minus 0 by R11 plus V1 minus V2 by R12 is equals to current entering, which is I1, right? So now on the LHS we'll write current entering, sorry, current leaving. On the RHS we'll write current entering. So now resistors will write in terms of conductance. So we'll have G11 into V1 plus G12 into V1 minus V2 is equals to I1. So now I can write this in a better way, which is G11 plus G12 into V1 minus G12 into V2 is equals to I1. So this will be my equation 1, which I have obtained from the node 1. So now we'll apply KCL at node 2 and see what equation we will be getting. KCL at node 2. So now we'll write the same thing. What we'll be write is current leaving is equals to current entering. So current leaving is V2 by R22. So I'll directly write, because V2 by R22 is nothing but G22 into V2, right? Conductance into the voltage difference is the current. So I'll directly write G22 into V2 plus this current, which is G23 into V2 minus V3. G23 into V2 minus V3. This is what current leaving is equals to current entering. Current entering is how much? V1 minus V2 into G12 is equals to G12 into V1 minus V2. Now I'll write in the same format. I'll segregate all the coefficients that are related to V1, V2, and V3. So how we will be getting? We will be getting something like this: minus G12 into V1 plus G12 plus G22 plus G23 into V2 minus G23 into V3 is equals to 0. So this will be my equation 2. So here we have equation 1, here we have equation 2. So now I'll apply KCL at third node to get my equation 3. So KCL at third node. Okay, so how we'll be writing? Same. Current leaving is equals to current entering. So current leaving is what? This is current leaving. These two are current entering. So V3 into G23. So V3 into G23 is equals to current entering is I3 plus G23. Sorry, this should be G33. I'm really sorry. This should be G33. R33. R33. So we have R33 meaning G33. V3 into G33 plus G23 into V2 minus V3. Now we'll bring that this side. So we'll have minus G23 into V2 plus G23 plus G33 into V3 is equals to I3. Got it? Is it clear until this point? Hello? Is it clear until this point?
Yes, sir.
Okay. Now these equations 1, 2, 3, they are called as nodal analysis equations, because these are the equations that we got by using nodal analysis. Now let us rewrite these equations in a better format. How? That I'll be showing you. So let me take this. Let me write it here. This is our equation 1 and this is our equation 2. So we'll write this in terms of a matrix. So equation 2. Okay, let me write it here only. And this is equation 3. So these are the nodal analysis equations. So these are the nodal analysis equations. Now we'll be writing this in terms of a matrix multiplication so that it would be easier to realize as well as easier to solve. So how we'll be writing? We'll be writing in a this format. So we have G11 plus G12, V1 coefficient, then V2 coefficient, then V3 coefficient in the first equation. Then V1 coefficient, then V2 coefficient, G12, G22, G23, then V3 coefficient minus G23, then again this is I think V1 or V2. This is V2, so first one should be 0. So 0 V1 coefficient, then V2 coefficient, then V3 coefficient, G23 plus G33 multiplied by V1, V2, V3 is equals to I1, 0 and I3. So this is like a matrix multiplication where this is a conductance matrix, right? These are all in terms of conductance. So this is like a conductance matrix G, and this is a voltage vector V bar, and this is a current vector independent sources or I. So we got G matrix into V vector is equals to I vector. So now if I have to solve for voltage, I'll do matrix inversion. So I'll do G inverse into I bar. So this is the final solution. So in order to solve for that voltage, I need to get this conductance matrix. So this is called conductance matrix. So this is called conductance matrix because it is a matrix consisting of the conductance of the circuit. Then this is called voltage, right? Voltage variable, like it's a variable, right? So it's a variable vector, variable vector. And these are all independent sources. Here there happen to be current sources, but these are all independent sources. So this is called independent source vector. Independent source vector. So now the aim is for any given circuit, I have to write it in this format, which is matrix G into V vector is equals to I vector. So that V vector I can directly write by doing the inverse of this G vector multiplied by the independent source vector. So this is the solution. So for this, I have to find G vector as well as I vector for any circuit. So here we have written the KCL and we got the this vector. But is it always mandatory to write the equations to get the matrix, or is there any shortcut to do the same? So until this point, is this clear, or do you have any doubts?
Excuse me, sir.
Yes.
Sir, if you just go a bit up, sir.
Okay.
Here only at the last step of this. Here, sir, if you want to find a V1 there,
Yes.
we have a G1, G11 plus G12
Yes.
minus G12, right
Yes.
now, sir?
Yes.
How to find here V1, sir, then? So
The
V is equals G inverse of I know.
yes.
So after calculating G inverse,
Yes.
how we need to find the V1 there, sir?
V1.
Yes, sir.
Okay. So after
If you
doing
want to
G
find
inverse
only
into I
the
bar.
V1.
Yes. So basically here we are solving for the all three V1, V2, and V3. So after doing this G inverse
Okay.
into I, you will get a, it's a
Total
good question
voltage
that
there.
you have asked. So this is 3 cross 3, right? And this is 3 cross
Yes, sir.
1. And this is 3 cross 1.
Yes, sir.
So
Because
now G inverse into I bar is 3 cross 1, right? This is also 3 cross 1.
yes, sir.
So by doing this inverse multiplication and multiplying, you'll directly get V1, V2, and V3 solution. V1 equals to this, V2 equal to this, V3 equal to this. So you are basically solving for all
So
these three.
directly there will
Yes,
get.
yes, directly we'll be getting.
Okay.
So that is the
Okay,
advantage
sir.
of writing it in the matrix. Now this either you can do it by yourself if it is a smaller matrix, or you can use some computer to do the inverse matrix multiplication for the same. I use MATLAB, but uh, in your exam as it is not allowed, they'll not go beyond 3 cross 3 matrix. But in my work, I do basically do higher order matrix inversion. So for that, we use some toolbox. We use MATLAB toolbox to do the same.
Yes, sir. Thank you.
Okay. Yeah. So now is there any, first of all, here conductance matrix is 3 cross 3 because we have applied three nodal equations because our nodes are 4. So the size of this is basically n minus 1 cross n minus 1 because n nodes are there, we'll get n minus 1 equation. So that's why the matrix size is n minus 1 cross n minus 1. So now this is called conductance matrix. Now the basic question is there any shortcut to do the same? Yes, there is a shortcut which we can follow to do the same. So for that, let me redraw this circuit. And now we'll use the shortcut and we'll get the conductance matrix. So conductance matrix. So conductance matrix is a matrix and each element can be considered as Aij, right? A11, A12, A23, A24, which is like ith row and jth column, which you might have already studied in your maths, higher secondary maths. So it is like a generalized element of this matrix, ith row and jth column. So two things you have to remember. One thing is if it is AII, which means the diagonal element. Diagonal element, it will be the sum of the conductance connected to that node I. So you can say that total conductance at node I. So now if it is say Aij non-diagonal element such that I is not equals to j, which means it is not diagonal element, then it will be negative of the conductance between node I and node j. Okay, so now using the same example, let us try to do the right. Let us try to write the conductance matrix. Okay, so now first let us draw the conductance matrix. So it's a 3 cross 3. So we have a 3 cross 3. So we have said that if first we'll write the diagonal elements. Diagonal element says the conductance connected at the node I. So node I, what is the conductance? Total conductance. Here we have one conductance. Here we have one conductance, right? Here the conductance is 0 because resistance is infinite for this current source. Agree? So the total conductance is G11 plus G12. Agree? This one plus this one. Agree? Conductance summation is this plus this. These two are connected to this node, right? Hello? Hello? Hello, can you hear me? Hello. Are you following? If you have any query, you ask. Else it will be difficult for me to understand whether you are following or not. Did you understand what I was saying here, or you want me to repeat again? Okay, let me repeat again. If it is a diagonal element, which means this element, and this element, we'll get the element value as the total conductance at node I. As it is A11, which means node 1, the element value is given by the total conductance at this node. The total conductance at this node is summation of this conductance plus this conductance, which is G11 plus G12. Now, if we come to node 2, we have conductance 1, conductance 2, conductance 3. So we have G12 plus G22 plus G23. Now, if you go to the third node, we have G23 plus G33. So here we have G23 plus G33. Now this is A12. A12 is what? Negative of the conductance between node 1 and node J. So what is the conductance between 1 and 2 element? G12. So here we will get minus G12. And between node 1 and node 3, there is no resistance, so it is 0. Similarly, now it is between the node 2 and node 1. So it will be minus G12. And now it will be between node 2 and node 3, which is R23. So here we have minus G23. Now again, we have between node 3 and 1, it is 0, and here it is node 3 and node 2. So if you see, this is a symmetric matrix. Now this into the variables V1, V2, V3 is equals to the independent sources, right? How will I write the independent source values? It is the currents entering that node. So what is the current that is entering the node? Independent source. It is I1, right? And in the case of node 2, it is 0. In the case of node 3, it is I3. I3. So that's how we use the shortcut to get this equation. So this is currents entering the node. So if you see, this matrix equation and this matrix equation are the same. Here we have gone through the pain of writing all the equations, whereas in this case, we have directly used the technique and we directly wrote the equation to get this matrix. Now we'll do the inverse of this and multiply with this to get the V1, V2, and V3. Is this clear, or do you have any doubts? Hello, are you following?
Yes, sure.
Okay. So, are you understanding, or am I going a little bit faster? Is it difficult? Be honest. If you don't understand, you tell me so that I'll explain it again. The point of this session is to make you understand. Yes, sir, understanding. Okay. So now let us solve one quick problem. So we'll solve this. So it is just similar to the question that the concept that we have just now discussed. So this will be our problem one for today. So this will be our problem one. So if you see, it's a conductance matrix. So all the resistance values should be converted into conductance. So 5 kilo ohm means how much? 0.2 millisiemens, right? I'm not writing the unit because there is no space here. And 2.5 is how much? Zero point 0.4 millisiemens. And 5 is 0.2 milli. 2.5 is 0.4 millisiemens. And 2.5 is again 0.4 millisiemens. So now this they have given node 1, node 2, and this is node 3. So we have to write the matrix conductance matrix G into V vector is equals to I vector. So we will be writing using this. So diagonal element first we'll write, which is the total conductance at the node I, and then non-diagonal elements is the conductance between the node I and node J. And on the RHS I vector, we'll write the currents entering that particular node. So now we'll start writing this matrix 3 cross 3. So first we'll start with the diagonal elements. So A11 means the total conductance at the node 1. So can someone tell me what is the conductance at the node 1? I see there are two conductance, 0.4 m and 0.2 m. So what is the total conductance at that node? Node 1, this node.
0.6.
0.6, yes. And node 2? which is this node. You have to see on the left side, on
It's
the right side.
minus point 4. No, sir.
No, no, I'm asking about this diagonal element. A22. A22. First
Here,
we'll
okay,
do
okay.
diagonal elements. So the total conductance at the node 2. So you should see all the resistance that are connected to the node 2 and add the conductance.
Yes.
So how much is it?
Point
zero point 0.4 plus
1,
zero
sir.
point 0.1. So someone has
1.
mentioned in the chat zero point 0.8. Fagim, it is zero point 0.4 plus zero point 0.4 plus zero point 0.2 because there are three resistors connected. So it is 1 milli. And then at the node 3, what is the overall conductance?
0.8, sir.
zero point 0.8. Yes, you are right. So we have zero point 0.8 milli. Now, what is the conductance between node 1 and node 2? And we have to add one negative sign of that for that. A12. So basically we are doing A12. So A1,
Minus point 4.
yes, minus zero point 0.4 milli. So A12 is minus zero point 0.4 means A21 is also minus zero point 0.4. Now what is A13? What is the resistance
0, sir.
between node 1 and node 2? Resistance is infinite, conductance is 0. Or maybe we'll use the same color so that people will easily understand that they're matching. So now what is A23? Conductance between node 2 and node
Minus
3.
point 4. Minus
Minus
point
zero point 0.4. Yes. Minus zero point 0.4 minus zero point 0.4 milli.
4.
And multiplied by the variables V1, V2, V3 is equals to, now comes the difficult part or the tricky part, which is the currents entering the node. So can you tell me what is the net current entering the node?
1 milliamps.
Yes, you are right. 1 milliamp. And at node 2, what is the current entering? You have to see all the sources. How many, first of all, how many
Sorry,
sources
sorry.
are connected to node 2? Two or three or one?
2, no, sir.
Are you sure?
2,
2,
no, 3,
sir.
3.
Three, right? 2
3,
milli,
3.
3 milli, as well
3,
as
3.
4 milli.
Yes.
If you see all these are connected to node 2. So this is how like we lose marks. So we should be very careful. Now, how much is the total net current entering? You have to see 4, 3 and 2.
Minus 5, sir.
Are you sure? Is 4 entering or leaving?
It's entering, no, sir.
Okay, so
It's
plus
minus
4.
4.
Plus 4, right? Current entering is
Entering,
positive. Entering is positive.
entering is
Current
positive
entering the
means
node
it's
is positive
currently
because
leaving.
this is
Yes.
I1, I3, both are positive. Here also 2 milli and minus 1. So plus 1 milli. So current entering means plus 4. This is plus 3 or minus 3. So how much is the net current entering this node?
5, sir.
Yes, 5. Uh, I hope others. Fagim, it is plus 5. You got the value right, but the polarity, you should be careful. It is plus 5. Yes. And at node 3, current entering. Fagim is saying minus 14. Others agree with him. Hello. How much is the current entering?
Minus 14. Minus
Minus
14.
14 milli. Yes. Minus 14 milli ampere. So now we got the matrix. This is our G vector, I mean G matrix. This is our V vector and this is our I vector. So how will I be getting V vector now? We will be getting V vector is equals to G inverse into I vector. So first let us go and check whether whatever matrix we have obtained is it correct or wrong. So we got zero point 0.6 minus zero point 0.4 and one more thing, you have to see how they have asked you to enter. So you have to follow these instructions and do accordingly. So they're saying write the answer in milli. Right, so that's why there is no M here. So you have to write in this string, and while entering, please be careful. They are asking you to put semicolon also. So you follow these instructions strictly, and then you enter the answer, else you will lose the marks. And this is the critical mistake that everyone will do. So you have to enter row wise. So the answer is zero point 0.6 minus 0.40, zero point 0.6 minus 0.40, and then we have minus 0.41 minus zero point 0.4, minus 0.41 minus zero point 0.4, and then we have 0 minus zero point 0.4, zero point 0.8, 0 minus zero point 0.4 and zero point 0.8. Now they are asking determine the voltage at the node 3. So that you will be obtaining by doing this inverse matrix and multiplying with the I bar. I will not be doing that inverse because this is just a mathematical calculation that you can do after this session also, because that you are going to get it anyway. It is just some inverse, but I'll write the value that I got V1, V2, so that you can cross check in the later time whenever you are free. But I'll not be solving because this is just some inverse that you can do it. I trust that you can do. So 0 minus 2.5, these are the values that I got, minus 18.75. So basically they're asking what is the value of V3. Again, there is less than a minute. If this meeting ends, kindly join back so that we can discuss the further theory. Minus 18.75 volt. So this is the voltage V3, and let us go back and check. So the voltage is minus 18.75 and it is lying within the range. So is this clear until this point how to get this matrix if it consists of only resistors and current sources? Now we are slowly going into some border cases where it is not so straightforward. Is this clear until this point? So any doubts till this point for this until this first problem? Do you have any more queries like how to get this matrix? This inverse I am not showing because it is easy, and I can uh, believe that you can do it. So you forget about this part, but until this part, how to get the matrix? Is it clear, or you still have any further queries? Clear, sir. Okay. Now we are going into the next problem. So we'll see the problem number 2, meaning problem number 3. So if you see in this problem, what is the difference along with the current source and resistors? There is one more element, which is a dependent source. Can you identify which dependent source is this? Anyone? So there is a dependent source. Can you identify which dependent source this is?
Current controlled current source, sir.
Current control or voltage control?
It's current only, sir.
So,
Voltage means there will be plus and minus.
so this current is dependent on a voltage or current?
Current only.
Zero point 0.4 milli into Vx, right? This
Okay. Okay. And then voltage, sir, voltage.
yes, yes, yeah. So it's a voltage controlled current source. So we have voltage controlled current source as well. So now what happens is this is not a dependent source. So usually when we are writing an A expression on the RHS side, we have currents entering the node which are independent in nature, right? So these are all independent. Now we have a current source which is dependent. So what or how we are going to address? First of all, if you see at node 1, at node 2, nothing will change. Whatever uh, theory or the shortcut that we have learned, it will still remain the same. But only change is going to happen at node 3 where there is a dependent source. So first we'll write the node 1 and node 2 equations. So how we are going to write? We are going to write in terms of conductance. So first let us write this in conductance. Zero point 0.2 milli, zero point 0.5 milli, and this is again 0.2 milli, Siemens, and this is zero point 0.4 milli, and this is also zero point 0.4 milli. So now, uh, how to write the equation at node 1? First one is the diagonal element, then next one is the negative of the conductance between node 1 and 2, and negative of the conductance between node 1 and 3 into V1, V2, V3 equals to the current entering the node, right? So instead of writing in the matrix, now we'll write in terms of the equation. So can someone tell me what will be the equation at node 1? So first will be the diagonal element, right? Diagonal element is the conductance at the node I. Agree? Total conductance. Hello? Are you following? Yes, sir. Zero point 0.7. Sorry, I made a mistake. So zero point 0.6. You are right. So zero point 0.6 milli into V1, millisiemens, but I am not writing the units. V1. And for V2, what we'll be getting? Negative of the conductance between node 1 and 2, which is what? Minus zero point 0.4, right? Minus 0.4 milli into V2. Next, conductance between node 1 and node 3, which is 0, is equals to current entering the node 1. How much is the current that is entering node 1? Hello?
minus 0.9.
Yes, is minus 0.9 milliampere. Minus zero point 0.9. Fagim, you are right, but there is a minus sign because this is current leaving and we are talking about current entering. So node 1 is fine. Now let us come back to node 2. So we'll write the same thing. First, we'll get A21. A21 is what? Negative of the conductance between node 1 and 2. So what is that value? Negative of the conductance between the node 1 and node 2.
Minus 0.4.
Minus zero point 4.
Milli.
Yes. Minus zero point 0.4 milli V1. And at V2 is A22, which is the summation of the conductance connected to node 2. Anyone?
0.8.
Zero point 0.8 plus zero point 0.2, right? 0.4 plus zero point 0.4 plus zero point 0.2.
It is I
Yes.
Nice.
So it is how much?
1, sir.
1. Yes. So plus 1 milli into V2. Then A23 is the negative of the conductance between node 2 and node 3. So what will be the value?
Plus 0.4 milli.
Plus point minus zero point 0.4 because there is a minus sign. So minus zero point 0.4 milli into V3 is equals to current entering node 2. So now can you tell me how much is the current entering node 2?
Minus 3.6.
Minus 3.6. Yes, you are right. So now this completes two equations, node 1 and node 2. At node 3 also, we'll write in a similar way. So conductance on the LHS and currents on the RHS. So first one is this 0, right? So here if it is 0, meaning here also we'll get 0. Then here it is minus zero point 0.4 means here also we'll get minus zero point 0.4 milli. Agree? Into V2 we will get. Now plus conductance at the node 3. Summation of the conductance at node 3. How much is the summation of conductance at node 3? We have two resistors. Hello. Zero point 0.8 milli. Yes. Forgive me, you are right because there is zero point 0.4 here and zero point 0.4 here. So it is 0.8 milli into V3 is equals to current entering. So what is the current entering? There are two currents. One is independent, one is dependent. But let me know the overall expression. After that, I'll tell you what to do. Uh, minus 0.4 Vx minus 14.4 milli. Yes. So current entering is minus 14.4 milli minus 0.4 milli Vx. Everyone agree with this? Hello? Everyone agree with this? Or do you have any
Yes, sir.
queries? Yeah. So now what is Vx in terms of V1, V2 and V3? Can someone tell what is the value of Vx in terms of V1, V2, V3? So Vx is the voltage between which and which node?
Between 1 and 3.
So what is the expression of Vx in terms of V1 and V3? V1 plus V3, V3 minus V1,
V1,
V1?
V1 minus V3.
Yes. So now
V1
we got
minus.
Vx is equals to V1 minus V3. So the same we are going to substitute it here. So we'll get minus 14.4 milli minus 0.4 milli V1 plus 0.4 milli V3, right? So now node 3 is going to change. Other nodes remain the same. So here we have 0.4 milli V1 minus 0.4 milli V2 minus or plus 0.4 milli V3 is equals to minus 14.4 milli. Agree? I have just simplified it. Agree?
Yes, sir. Yes, sir.
Okay, so now these are my new equations. Equation 1, equation 2, and equation 3. So now using these three, we have to write in terms of matrix because they have asked in terms of matrix. So let me write. So we have 0.6 milli into V1 minus 0.4 milli into V2 and then 0 and then minus 0.4 milli, then 1 milli, then minus 0.4 milli, and then finally we have 0.4 milli, then minus 0.4 milli, then 0.4 milli into, so this is our conductance matrix multiplied by V1, V2, V3, V1, V2, V3. This gives us what is there on the RHS side, which is minus 0.9 milli, minus 3.6 milli, and then minus 14.4 milli. So is it clear until this point? Hello?
Yes, sir.
Yeah. One thing I'm writing, it is no more symmetric because there is one dependent source and it is only at some node, particular node, it is not going to be symmetric. Say if this expression is 0, then we'll have zero point 0.6 minus 0.40 minus 0.41 minus 0.40 minus 0.4 0.8. So this matrix is symmetric if this Vx is equals to 0. Say if this element is not there, then this is symmetric. But because this is there, in particular row, some of these values are getting changed, and because of that, the matrix is no more symmetric. So one thing you have to remember is this conductance matrix is symmetric if there is no dependent source and if it is only current sources and resistance. If it is not the case, then it uh, cannot be symmetric. So it is not expected to be symmetric. Is that clear? Symmetric means what happens, sir? So symmetric means, yeah. So let us take this example only because it is symmetric. So this is a symmetric matrix. Symmetric matrix. So for a symmetric matrix, what happens is Aij is equals to Aji. So ith row jth column element is same as jth row ith column. Or you can directly say if this is a diagonal, then these two will match, these two will match, and these two will match. So if you draw a line passing through the diagonal, the elements on the left side and the right side of the diagonal will match. So because if I have to write, this is A11, this is A12, this is A13, and this is A21, and this is A22, and this is A23, and this is A31, this is A32, and this is A33. So A12 should match with A21, A13 should match with A31, A23 which should match with A32, and A11 means A11. So there is no other element. So this is what a symmetric matrix. These are the characteristics of a symmetric matrix. If a matrix is following this Aij equal to Aji, then it is called symmetric matrix. Is that clear? Yeah, okay, sir. So, so here there is one voltage source. Sorry, there is one current source, voltage dependent current source, and because of that, there is some change in the matrix, and it is no more symmetric. So first we'll check whether the matrix that we have obtained is correct or is there any issue. So again we'll check. First we got zero point 0.6 minus zero point 0.40, zero point 0.6 minus zero point 0.40. Then minus 0.41 and minus zero point 0.4, minus 0.41 and minus zero point 0.4. Then we have zero point 0.4 minus zero point 0.4, zero point 0.4, zero point 0.4 minus zero point 0.4, zero point 0.4. So we got. So I'm not going through these details, but you please follow these instructions. Must follow. If you see, do not have any space at the start of the line. So while entering this string, you should be very, very careful and you should not do any mistakes and have exactly one space between entries on each row. So after zero point 0.6 and minus zero point 0.4, you should have only one space and do not have any space after the last entry in each row. So after that last entry, 0, the semicolon should be there and there should not be any gap. And after this semicolon also, there is no gap. So you should follow the same instructions and else it will show as a wrong option. So you do not have any trailing zero. That is, do not write 5.5 as 5.5 or 5 as 5.0. So if it is 2.50, write as 2.5. Here we have zero point 0.6, right? So it should be written as zero point 0.6, not 0.60, and zero point 0.4, not 0.40, and 1 should be written as 1, not 1.0. So these are the instructions, because even after solving the entire circuit, if you have not entered the answer properly, then it will detect as a wrong answer, and it is a very serious issue. So you have to be very, very careful. So now I am directly writing these V1 and V2 and V3. I'm not going to solve, but you can solve. It is just a matrix inversion. So if you solve for V1, V2, V3, I'll just write what results you are going to get. This you can check in the later your free time. So we'll have minus 21.5, and this is minus 30, and this is minus 44.5. So these are the values that you are going to get. So now if these are the answers. So they are asking what is the power dissipated in the resistor Rx. So if I have the node voltages V1, V2, V3, how to calculate the power dissipated in the resistor Rx in this Rx? Anyone? Sir, IR, but I don't know the current through R. I know the voltage, right? Do I know the voltage across the resistor V2? So then which formula am I going to use, or which one should be used? Hema, any idea? Which uh, formula of power we can use. V into V by R. Forgive me, you are right. So V square by R. And which V? V2. V2 by Rx is 5K. So power dissipated. So power dissipated in 5 kilo ohm resistor is nothing but V2 square by R, which is 5K. So we'll get 900 by 5K, which is 180 milliwatt. So this is the final answer. That is the power dissipated in that resistor, 5 kilo ohm. So how much is the power dissipated? 180 milliwatt. So 180 milliwatt. So is this clear, everyone? This question, if there is a voltage controlled current source, how we are going to solve and how to uh, proceed further? Or do you have any other queries? Okay, let me just summarize. In the case of voltage controlled current source, as shown over here, we do not have directly independent current sources as well as resistor. Instead, we have one dependent current source as well. So in that case, what we are going to do, because there is a dependent current source at this node 3, node 1 and node 2 expressions will remain unchanged. Only the expression at node 3 will change. So node 1 and node 2 we have directly written using the shortcut method that we have learnt over here. And kindly note that this is very important, and you should remember this because this will save a lot of time. Don't think of writing KCL equation at every node because that will waste a lot of time. You are going to get the answer, but it will waste your time unnecessarily. So using that shortcut method, we wrote the expressions at node 1 as well as node 2. At node 3 also we have written the same, but there is a dependent voltage source. So we have later modified this by substituting the value of Vx, which is in terms of V1 and V3. And after substituting that, we have written it in terms of a matrix expression. And then we have solved for the voltages V1, V2, and V3. And then we have seen what other questions they have asked in the question paper or the assignment. And then we have solved for the power that they have asked. Is this clear until this point? If there is a voltage controlled current source, how we are going to deal? Or do you have any queries before we proceed further? Clear, sir. Okay. Other people, is it clear? I hope it is clear. So if you have any queries, please ask, else we'll move to another problem. So this has another type of dependent source. So which dependent source does this circuit have?
Current control current source.
Yes, you are right. So this is current controlled current source because there is a current source and the value of the current source is dependent on some other current Ix. So there is no difference basically. Here, whatever procedure that we have followed will follow the same procedure. What will be the difference? Here, the value of this current is dependent on a voltage, so we have substituted that. Here, it is dependent on some current, so we'll substitute that. So we'll proceed in the same way. There is no other confusion. So first, let me write this in terms of conductance. This is 1 milli. This is zero point 0.5 milli. Okay, and this is also zero point 0.5 milli, and again this is 1 milli, and this is also 1 milli. So we'll do the same thing. First, we'll write the KCL at node 1. So can anyone tell me? So at node 1 means we have A11, A12, A13. A11 means the conductance, summation of the conductance at node 1. A12 means negative of the conductance between node 1 and node 2. A13 means negative of the conductance between node 1 and node 3. So can someone help me with this? How to write this equation at node 1? A11 is the Total conductance at node 1. So how much are we going to get? Sir,
1.5, sir.
yes,
1.5 M.
yes. 1.5 m into V1. And A12 is the negative of the conductance between node 1 and node 2.
Minus 1.
Minus 1 milli, yes.
Minus
Minus 1
1
milli into
M.
V2. And then A13,
It's 0, sir.
0, yes. So we have plus 0 into V3 is equals to the current entering node 1. So how much is the current entering node 1?
1, sir.
1. Forgive, 2
Okay,
is
1
entering
milli.
and minus 1 is leaving. So it will be 2 minus 1.
1
So
is
1 milliampere.
1 milli.
Yes. Now at node 2, can you tell me what is the expression at node 2? First of all, A12, which is the negative of the conductance between 1 and 2.
Minus 1 M.
Okay. And then A22 is summation of the conductance at node 2.
2.5 M, sir.
2.5. Yes. So it is plus 2.5 milli
Plus
into
2 point.
V2. And then the last term
Minus 1 M.
minus 1 milli
1
because
and V.
between 1 and sorry 2 and 3 there is 1 milli conductance. 1 millisiemens. Basically, I'm ignoring that as it will look complicated in the equation. That's why I'm removing. And what is the total current entering node 2?
It's minus 1, sir. Minus 1
Min-
M.
minus
1 M.
minus 1. Yes.
1
Fagim,
milli M.
you are also right. It is minus 1 milli. So how much it is? Minus 1
Minus
milli
1 milli.
ampere. Okay.
And
Now we'll go to node 3. So now node 3, first we'll get A13, which is the conductance connected between node 1 and node 3. So what will be the value of that?
it's 0 V1, sir.
0 V1, yes. And then second term between 2 and 3,
My, minus 1 M.
yes, minus 1 milli. And at 3, the summation of all the conductance at
Summation.
element 3.
2 M, sir. 2 M.
Yes, yes, 2 milli plus 2 milli into
Plus 2.
V3. And the current entering the node 3, how much is the value?
It's 3 M plus 2 IX, sir.
Okay, 3m plus 2ix.
3 milli plus 2 IX.
3 milliampere plus 2ix. Okay. So now we'll going to do the same thing what we have done in the previous problem. We'll substitute the value of ix. So what is the value of ix? Can someone tell? This is the value of ix. So ix equals to 1 milliampere. Fagim has said ix equal to 1 milliampere. How is it 1 milliampere? Can Fagim please explain how is it 1 milliampere? 2 minus 1. Ix, this is the ix. Ix is current flowing through 1 kilo ohm. Anyone? Uh, Hema, what is the value of Ix? So say we want current. So what do we
It is,
voltage by
we
resistance?
should consider some current through 2 kilo ohms, sir.
Okay.
Then the 1 milli minus that current will be IX, sir.
Okay. Or if I want to write in terms of V1 and V2, can you tell me what is the value of Ix?
Then it will be
V1 minus V2 by
0, no.
1 kilo.
Yes, yes. So it is V1 minus V2 by 1K. Agree?
Oh, yes,
Yes. So now I'll write this as 1 milli into V1 minus V2. Agree? Fine. Yeah. So basically, I want Vx in terms of V1 and V3 because I'll manipulate the expression and then I'll make my new matrix. So here also I want Ix in terms of V1, V2, V3. Here it happens to be 1 milli into V1 minus V2. So if you substitute that, so basically we are just substituting Ix in this expression. Then we'll be getting 3 milli plus 2 milli V1 minus 2 milli V2, right? 2 milli V1 minus 2 milli V2. Agree? I have just substituted the value of Ix in this expression. As someone said, you can also write in terms of 1 minus V by zero point 0.5. That is also fine, but that will be a little bit complicated, or you can also proceed with that. There is no harm in that because KCL is anyway applicable. So it will also give the same result. So is this fine? How I am getting this expression? Okay, sir. Yeah. So now I'll just manipulate this and I'll write in a different way. So I'll be getting minus 2 milli V1 plus 1 milli V2 plus 2 milli V3 is equals to 3 milliampere. So now we have equation 1, equation 2, equation 3. These are my new three equations using which I have to get the matrix expression. Is that okay? We got these three modified equations. Fine. Hello.
yes, sir.
Yes. Okay. So now let us write in terms of matrix format. So we have 1.5 milli minus 1 milli, then 0, then minus 1 milli, then 2.5 milli, then minus 1 milli, then we have minus 2 milli, 1 milli, then 2 milli. This is the conductance matrix into V1, V2, V3 is equals to the values 1, minus 1 and 3 milli. 1 milli, minus 1 milli and 3 milli. So again, if you see, the conductance matrix is not symmetric. This is not symmetric because of the dependent source again. Okay, so let us just first verify whether the answer is correct or wrong. So we have 1.5 minus 1 0, 1.5 minus 1 0, then minus 1 2.5 minus 1, minus 1 2.5 minus 1, and then we have minus 2 1 and 2, minus 2 1 and 2. Now they are asking again the voltage at node 3. So first we got the matrix. So this can be written as G into conductance matrix into V bar is equals to I bar. So from this we can get V bar is equals to matrix G inverse into I bar. So you can check it later, but I'll just give you the V1, V2, V3 expression so that later you can check. Now let us not waste the time because we can discuss more problems by skipping this calculation, which you can do later as well. We'll get as 1.4, 1, 1.4 volt, 1 volt, and 2.35 volt. So this is the voltage that you are going to get. So now let us see. what they have asked and how much we are getting. What is the voltage at node 3? So we are getting voltage, we are getting voltage at node 3 as 2.35. So 2.35. So it is in between 2.3 and 2.4. So it is perfectly matching with whatever we have obtained. So let me just summarize what we have discussed in this problem. So in this problem, we have current control, current source. Previously, we have voltage control, current source, but both are current sources. And we have seen that this current source is at a particular node, at node 3 in this case, at node 3 in the previous case as well. So we can see that only the equation at node 3 is going to change and other two nodes equation will remain the same. So we can apply the technique or the shortcut that we have learned here, and we can write the expressions or the equations for these two nodes, node 1 and node 2. Here in this case, node 1, first term is A11, which is the sum of conductance at node 1, which is zero point 0.4 plus zero point 0.2, 0.6 milli. And A12 is the negative of the conductance between node 1 and 2, which is minus zero point 0.4 milli. And A13 is the conductance between 1 and 3, which is 0. So 0 is equals to current entering, which is minus zero point 0.9 because zero point 0.9 is leaving. Similarly, at node 2, we have minus zero point 0.4 coming over here because A12 and A21 are same. And A22 is the summation of conductance at node 2, which is zero point 0.4 plus, sorry, I think I'm explaining the other problem. I'm really sorry. So at node 1, we have 1 plus zero point 0.5, so 1.5. At node 2, between 1 and 2, we have minus 1 milli. Between 1 and 3, we have 0. And between 2 and 1, we have minus 1 milli. And between at 2, we have zero point 0.5, 1 and 1, 2.5. Between 2 and 3, we have minus 1 milli. And node 3, we have 1 and between 1 and 3, we have 0. Between 2 and 3, we have minus 1 milli. At 3, we have 1 milli plus 1 milli, 2 milli. At node 1, current entering is 2 minus 1, which is 1. At node 2, current entering is 1 minus 2, which is minus 1. At node 3, current entering is 3 plus 2 ix. Now ix we know, which is 1 milli into V1 minus V2, because current is nothing but voltage difference by resistance, as current is flowing from V1 to V2. So V1 minus V2 by 1K. Now after substituting this, we have re change this expression to write in terms of AV1 plus BV2 plus CV3 is equals to some constant current I naught. After that, we got the modified three equations of this circuit. Now I have written it in terms of a matrix multiplication as G into V vector V is equals to I vector I. So after getting this, we have first verified whether whatever we have obtained, whether the answer is correct or wrong, and it is correct. After that, we have seen that in order to get the voltage vector V, we have to do the inverse matrix multiplication with I vector, which I have not done now. You can do it later and check the values, as this video will be uploaded in the YouTube. You can always check. And then we got V1, V2, V3, and then we have checked whether V3 is matching or not, and it is perfectly matching, and it is 2.35. So with that, we have completed three problems. Now we are going to solve another problem. There is less than a minute. If this meeting end, kindly join back. Then we can start discussing the next problem. Do you have any doubts until this point? First of all, are you following? I don't see many people today. Also, only two people are responding. What happened to the other people? Are you not following, or is it? Are you not understanding? Or if this meeting ends, kindly join back. Brindu Kumar, are you following? Okay, now we are going to solve another problem. So in this problem, we have a voltage source, uh, independent voltage source, along with the resistors and current sources. So this is our next problem, which has a independent voltage source as well. Are you able to see my screen? Hello. This is our problem 4. Are you able to see my screen?
Yes, sir. Yes.
Okay. Okay. So this is our problem 4, and it has independent voltage source. So what is the issue with the independent voltage source? The issue with the independent voltage source is we cannot get the current flowing through that, because if I ask you what is the current through this, I cannot say, because I cannot write this current is equals to conductance into the voltage difference, because I know the voltage difference between 2 and 3, but how am I going to get the conductance? Conductance is how much? Infinite, because resistance is 0, but I cannot write. So the problem is that we cannot get the expression for the current flowing through the voltage source. We cannot directly get it. But what is the benefit that we are going to get? We can directly get the expression between V2 and V3. So, if the voltage source is connected in this way, can you tell me what is the relation between V2 and V3 in terms of this voltage? Sir, V2 minus V3 is 11. Is it correct? V2 minus V3 or V3 minus V2? Which is at higher potential? Minus V2 plus V3, yes.
V3.
Yeah. V3 minus V2 is equals to 11. Okay. Now, we got already one equation, right? Now we have to get two more equations, because we need three equations as there are three unknowns. Okay, first we'll convert everything into Siemen, millisiemen, 0.5 milli, 1 milli, then 2 milli means 2 means 0.5 milli, then here also 1 milli. So at node 1, nothing is going to change because there is no voltage source. So at node 1, everything remains same. Okay. So at node 1, can someone tell me the expression A11, A12, A13? What is A11?
It's 0.5.
0.5 or total conductance at node
0.5 M. 0.5 milli V1.
1. Is it 0.5 or 1.5?
Total, sir.
Yes.
Total is 1.5.
Yes, yes. So 1.5 milli V1 and A12, which is negative of the conductance between 1 and 2,
Minus 1 milli V2.
minus 1 milli V2 and A13.
0 V3.
Yes, 0.
Yes,
Yes.
0.
Yes, Fagim, you're also right. Plus 0 into V3 is equals to current entering. How much is the current entering? 11. Yes, you're right. 11
11.
ampere. Yeah. Yeah. So now node 2 and node 3, we cannot directly write the expression at node 2 and at node 3. So what we will do is, if there is any voltage source between 2 and 3, then we use something called super node, which means we'll combine both node 2 and both node 2 and node 3, and this is called super node, meaning we'll ignore the voltage source between these two and apply the nodal analysis expressions here and as well as here by ignoring this, and we'll get one equation out of this, because we are considering or combining both node 2 and node 3. How many equations we'll be getting? We'll be getting here one equation from this. So how we are going to write that, I'll going to explain. So total how many equations we have? We have 1, 2 as well as 3. So now using these three equations, we have three equations, three unknowns we have to write in terms of the matrix, and uh, that should be it. So let us take this. Control C, and Control V. So we have to write this expression at the super node, right? So s- so base so basically we will be considering the equations at node 2 and equations at node 3 by assuming that this is entirely a common node. So we'll consider this as one node, which is the super node. Is it clear until this point what we are doing basically? Yes. So when we consider as super node, so first we'll write all the equations related with the node 2, and then we'll write all the equations related with the node 3. Okay. So now we'll start with the node 2. So when we write node 2, what all we usually do, A2 means A12, A22, and A23. Similarly for 3, A13, A23, A33, right? So can you tell me what is A12? A12? Minus 1 milli. Yes. So minus 1 milli into V1, and then A22.
Hmm.
Others are following, right? Hema, are you following?
Yes, sir. Yes.
Okay. So now first time, maybe I'll just write it in this way. Node 2, right? First, I'll use two colors. Uh, Orange is for node 2. So node 2, I'll use orange, and the dark green I'll use for node 3. First I'm writing at node 2. Node 2 we have A21, A22, A23, right? So minus 1 milli into V1 plus what is the total conductance at node 2?
It's
1.5 V2.
1.5.
Yes, 1.5 milli V2. And A23, there is no connection as such, right? Between 2 and 3. And we are ignoring the connection between 2 and 3 and considering both as a single node, which is super node. So there is no expression between V2 and V3 because there is no direct resistor connected. Okay. So sorry, as mentioned, this should be in the orange color. So let us write this in the orange color. Okay. Now comes the third node, which is 3. So now what is A13 and what is A33? Because A23 there is no point because 2 and 3 we are considering as a single node super node. So what is A13?
It's 0, sir.
0. Yes. So we have 0 V1. And what is A33?
Minus 1 millimeter.
Is it minus or plus? Fagim, are you
Plus,
sure?
sir.
Is it 1.5 or only at node 3? Only at node 3. 1 milli. Right? Hema, do you agree? 1 milli,
Yes,
right?
sir. I got
Yeah.
confused. Yes.
So we basically are writing separately at node 2 at node 3, but we are combining it as an expression. So this is node 2. When we say node 2, and then when we say node 3, so at node 2, we have considered this and we have considered this. At node 3, we have only considered this. But we are writing, combining it as an equation because we are considering both node 2 as well as node 3 as one single node, which is a super node. So now this completes the LHS side of the expression. Now if we go to the RHS side, we have to consider the currents entering the node 2 plus currents entering the node 3 because we are considering both nodes as a single node. So now can you tell me what is the current entering the node 2? Which means I'll consider this one and this one. So how much is the current? Again, I'll use this
Minus 4,
orange
sir.
color,
Minus.
minus 4. So minus 4 milli ampere. And node 3, how much is the current entering? I'll use this color,
Minus 18.
minus 18. Yes. So minus 18 milliampere. So now let us rewrite this expression. We have minus 1 milli V1 plus 1.5 milli V2 plus 1 milli V3 is equals to minus 22 milliampere. So this is going to be our expression 3. So first I'll write this expression. So we'll write it like this. And if we see, okay. So this is our expression, uh, one expression, and this is our another expression. And this is our last expression. So it is V3 minus V2 equal to 11. So I'll write it as V2 minus V3 minus V2, right? So minus V2 plus V3 is equals to 11 volt. So now you have to be careful, right? Uh, Here the unit is milliampere and here the unit is volt. So that should be very clear. So first we got it at node 1 and then we got the expression at super node. Then we got the expression at voltage source. So is this clear until this point? Is it clear?
Yes, sir.
Yeah. Now let us write this in terms of the matrix. We have 1.5 milli, then minus 1 milli, then 0, then minus 1 milli, then 1.5 milli, then 1 milli, then 0, then minus 1, 1. If you see, the first two rows has milli in the expression, whereas the second row and the third row, the third row, they don't have. Only 1 and the 2. These two rows has milli, and the other row, which is the third row, it doesn't have. Similarly, if we come to the RHS side, first one is 11 milliampere, second one is minus 22 milliampere, third one is 11 volt. So this you have to be very careful. Okay, so now we got this matrix, which is the matrix G times vector V is equals to, sorry, I bar. Now let us go and check whether whatever we have solved, it is correct or wrong. So we
Sir,
have,
that 11 is
sorry,
voltage.
sorry.
Sir, that 11 is that one voltage, no, sir. You have
Yes,
written the current.
11 is voltage. But I is
That we
actually
have written.
independent source, not independent voltage or current source. I is independent source. It may be current, it may not be current. Is that clear? Okay.
Okay,
So
even though
now
if
we
it
have
is
pointed
voltage,
out,
also we.
yes, let me write one important thing. So this is Siemens. This is also Siemens. This is also Siemens. This is also Siemens. So that's why this is ampere, and this is volt. So now the dimensions are properly matching, right? Because this is not just a constant. This has a dimension of millisiemens. So millisiemens multiplied by voltage gives ampere, and constant multiplied by voltage gives constant. So is that clear now? We have missed this dimension, so that's why it looks like this is dimensionless, and that is not true. This has dimension and this is dimensionless. Hema, is that clear now?
Yes, sir, yes, sir.
So now let us go and check. So we have 1.5. They are asking in terms of millisiemens for the first two, and the last one is scalars. So they are saying the G matrix entry should be in millisiemens if they are conductance or scalars as applicable. So if it is a scalar, then there is no unit millisiemens. So if it is scalar, you have to directly write it as a scalar. If it is Siemens, you have to write it in millisiemens. So we have 1.5 minus 1 0, 1.5 minus 1 0, then minus 1 1.5 1, minus 1 1.5 1, and in the last we have 0 minus 1 and 1. We have 0, -1 and 1. So we have to be very careful while entering the answer, which is the most critical part, because we have like done so many things, and while entering the answer, if you make any mistakes, then it is gone and you will not get any marks. So we have to be very careful. V bar is equals to G inverse into I. And I have solved. I'll just directly write the voltage that I have obtained, which is V1, V2, V3 matrix is equals to, how much did I get? -2, -14 volt and -3 volt. And while doing inversion, you have to be careful, because there is milli in two rows and there is no milli in one row. So my best suggestion would be to cancel this milli, milli, this milli, all millis you cancel. Now while inverting, there is no milli business, so you can directly invert. So G matrix will be 1.5 -1 0, -1 1.5 1, 0 -1 1, and I will be 11 -12 and 11. After doing this inversion and multiplying with I vector, you will get V1, V2 and V3. So what is the other question that they have asked? They have asked what is the voltage at node 2. The voltage at node 2 we have obtained as -14. So -14 is correct. So is this clear how we have solved? Let me just summarize. If there is any independent voltage source, the issue is we cannot directly get the expression for the current flowing through this voltage source. So we will not be directly getting the current through this. But one additional advantage is you can directly get the relation between V2 and V3, which is V3 minus V2 is equals to 11. At node 1, there is no issue. We have directly written this expression. At node 2 and node 3, we cannot do, or we cannot individually write the expression at node 2 and node 3. So we'll combine these two nodes and consider it as a single node, which is called a super node. And this node 2 and node 3 will give us in one equation. So while writing the expression at super node, first we have written the expression at node 2 on the LHS and node 3 on the LHS, and done the summation of these two. And on the RHS current entering, we have written the currents entering the node 2 plus currents entering the node 3, because we are considering these two as a single node, which is called a super node. So now at node 2, first we will write A11, A21, A22 and A23. Because node 2 and node 3 are considered as same, A23 is 0. So A21 is -1 milli, A22 is 1 milli plus 0.5, which is 1.5 milli. At A3 we have A31, which is 0, and A32 is no, doesn't make any sense because 3 and 2 are single node, and A33 is the conductance at node 3, which is 1 milli. This completes the LHS. On the RHS side, current entering the node 2 plus current entering the node 3, which is -4, -18, so -22. So we got one equation from the super node, one equation at the node 1, and one is from the voltage source, which will give us the conductance matrix. And you have to be very careful. You have to be very careful because two of these rows has milli and one row does not have milli. So I have cancelled all the millis, so there will not be any confusion. And after doing the inversion matrix and multiplying, you will get the V1, V2, V3 expression as mentioned over here, which you can check later. So someone has asked query, sir, why is supernode considered with respect to node 2? You have shorted node 2 and 3 nodes, but for node 3 separated. So we will do supernode for those two nodes between which the voltage source is connected. If the voltage source is connected between 1 and 3, we'll consider 1 and 3 as a supernode. When there is a supernode, how we are going to write this expression? First, we'll write the equation at node 2 separately plus node 3 separately is equals to current entering the node 2 plus current entering the node 3. So that's why I have written expression in these colors, because now you can see how I have written this expression. First, I have written the expression at node 2 in the orange color plus the expression at node 3 is equals to current entering the node 2 plus current entering the node 3. And why we have considered 2 and 3 as supernode? Because there is a voltage source between 2 and 3. So where between which two nodes there is one independent or dependent voltage source, those two nodes should be considered as a supernode. Does this clarify your questions? If 11 volt is reversed, then also same equation. Yes. If 11 volt is reversed, then also this equation will remain same. Only this equation will be changed. Here we will get V2 minus V3 equal to 11. So here we will get 0, 1, -1. Everything remains same. Okay, sir. Yeah. So if you have any queries, you can ask, else we'll move on to our final problem of today's session, which is dependent voltage source. Do you have any queries until this point? This is our last question. So it entirely looks same to our previous question, except instead of particular Vx, we have like a independent voltage source, we have a dependent voltage source. So the third expression that we got here, we directly got in terms of constant level. Here we will not get Vx directly. Here we will get in terms of V1 and V2, so that we are going to see how we can solve. So this is our how much? This is problem 4, right? This is 4, this is 3. So this is our fifth problem. Today, problem 5. Today's session is more of problem oriented. So that's why the theory I have covered for a few minutes. After that, we are learning using the problem. So that's why it is like this. But in the upcoming weeks, if it is like the theory has to be taught and then problems, then I'll do in that way. But if it is morely problem oriented, then we'll learn the theory using problems itself. So we have dependent voltage source. Dependent voltage source. Okay. So here I can write Vx is nothing but V2 minus V3. Agree? This minus this. Or do you have any query? Is it clear? Vx is equals to V2 minus V3. Are you there?
Yes, sir. Yes, sir.
Yeah. And what is Vx in terms of V1 and V2?
It's V1 minus V2.
Yes, V1 minus V2. So V1 minus V2. So now if I rewrite this equation, we will get V1 minus 2V2 plus V3 is equals to 0. So now here the very basic question is, sir, you have taken RHS to like LHS to the RHS side. What if I do RHS and bring it on the LHS side? Then you might say, sir, I will be getting a different equation, which is minus V1 plus 2V2 minus V3 is equals to 0. Both are the same, but if you see the constants, in one case it will be 1 minus 2 1, in another case it is minus 1 2 minus 1. So there is no issue. If you see the answer, we'll have both the expressions. So both are correct. 1 minus 2 1 and minus 1 2 1. So that's why this is also correct. This is also correct, because there is no that straightforward or any rule that this has to be taken on that side, that has to be taken on this side. So both are correct and both the answers are valid. So that completes our one equation. So now let us write this in terms of milli. 0.5 milli. This is 1 milli. This is 0.5 milli. This is also 0.5 milli. And this is also zero point 0.5 milli. So first at node 1, we can directly write without any issue. And it is also not supernode. Here also supernode is between 2 and 3, because there is a voltage source between 2 and 3. So at node 1, can someone tell what is A11, A12, A13 quickly? We are going towards the end of this session, so you should be able to tell it very quickly. A11, how much it is? Conductance at node 1, total conductance at node 1. 1.5, yes, 1.5 milli
1.5
V1. And A12,
minus 1 millimeter.
minus 1 milli V2. And A13,
It's 0.
0, is equals to current entering the node 1, which is how much?
13 milliamps.
Current entering is at node 1, 13, right? Yes, you're right.
13, sir.
Yes, 13 milliampere. Now comes our super node, which is node 2 and node 3. Okay, node 2, comma, node 3. So now this is our super node. Okay, so let us just take this down and we'll write the expression. Again, we'll use the same format. I'll use one color for one node and another color for another node. So it will be very clear if you go back and check. So now we have node 2 in orange color and node 3 in dark green color. So first we'll write node 2, which is A1, A22, A21, A22 and A23. So what is A21?
That one.
Sorry, A21. Hello.
-1 millilevel.
Yes, minus 1 milli into V1
V2
and A22 summation of the conductance at
plus
node 2
1.5
plus 1.5
plus 1.5 milli
milli
V2
V2. So that completes the node 2. Yes, Fagim, you're also right. 1.5 and minus 1. Now node 2 is done because A23 doesn't make any sense because 2 and 3 are same node, which is the super node here. So now at node 3, A31, what is A31? 0. Yes,
1
0
milli
V1. A31, A31.
A A310
0 and A23 also doesn't make any sense. Now what is A33? A33 is 1 milli, which you have mentioned
1
already.
milli.
Yes, 1 milli. Now coming to the right hand side, currents entering the node 2. What are the currents entering the node 2? Minus 12 plus 5.5. Yes, you are
minus
right.
6 minus 6.5.
Yes, yes. Minus 6.5 milliampere. And then current entering the node 3. Minus
Minus
2.6.
2.5.
Yes, 2.6 milliampere. So now this completes our supernode expression. Let us just rewrite it. Minus 1 milli V1 plus 1.5 milli V2 plus 1 milli V3 is equals to summation of 6.5 and 2.6. It is minus 9.1 milliampere. So let us just write. First one is the node 1, right? Our equation first is node 1. So node 1 is our first equation and then supernode is our second equation. And then these two are our equation 3. So any of this is true and you can follow any of these three. So if we write this, this is equation 1, equation 2 and both of three could be equation 3. So now if we write in terms of matrix, I have 1.5 milli, minus 1 milli, then 0, then minus 1 milli, 1.5 milli and then 1 milli. For the timing, let us just proceed with the first one, which is 1, minus 2 and 1. So now this multiplied by V1, V2, V3. This will give us 13 milli, minus 9.1 milli and then 0. So again the same thing. There are two equations with milli in their expression because there is Siemens here which we have not written, but these are not dimensionless. The bottom one is dimensionless. So this is ampere ampere and this is volt. So now this completes our matrix. Let us just go and check. So first row we have 1.5 milli. So 1.5 minus 1 0. 1.5 minus 1 0. And the other one minus 1 1.5 1. Minus 1 1.5 1. The last one could be 1 minus 2 1 or minus 1 2 minus 1. So ours is 1 minus 2 1. So this is also correct and our equation is true. So now if this is G matrix and this is V bar, and if this is I bar, we can get V bar as G inverse into I bar, and by solving that, you will get V1, V2, V3, which I have solved. You can check later. This you will be getting as 11.2, then 3.8, then minus 3.6 volt. So again, while checking or inverting, kindly cancel the milli, else you will make mistakes. So cancel the milli and then check. So in the question, they have asked what is the value of node 1. We got 11.2, which is matching. So this also remains the same if there is independent or dependent voltage source. First we'll get the expression based on that dependent or independent voltage source. Then you apply nodal analysis at that node where this voltage is not connected to. And if it is connected between node 2 and node 3, then you have to consider a super node and write the expression accordingly. Then this will give you one equation. Node 1 will give you one equation. That dependent or independent voltage source will give you another equation. And all these three will give you one matrix expression, and using that you will get the voltages. So this completes our session. Before I summarize, do you have any queries until this point? I see only two people are active today, Fagim and Hema. I think they are very much clear with the concepts now. I am not sure about the other people. If you have any doubts, you can ask, else I'll just summarize today's session. Any queries until this point? So this week is basically very simple if you understand the concept, but if you don't understand, you will face a lot of issues. Anyway, I will be uploading this video to the YouTube. So if you have any queries, you can go through this video, and if you have any doubts, you can mention in the comment section or you can reach out to me. Once you know the concept, it will take barely any time to write this expression and convert them into matrix multiplication. The only difficulty is while inverting the matrix. So I have not shown it today because it will consume time, and we would have not been able to cover these many problems. So that's why I have skipped that part. But I request you to do the matrix multiplication and try to do it by yourself, so that if you uh, face any difficulty, you will know where you are facing and how to tackle with the matrix multiplication, and you will also get some practice. So let me just quickly summarize what we have discussed today. Today we have started with the circuit analysis basic, that how many cases. Yes, yes.
Sir, can you go to the problem number 2?
Okay, problem number 2. This one, or which question? Hello, your voice is breaking.
This one, sir. This one.
Yes, yes.
Right, sir. This one, sir.
Okay, what is your query?
Hello.
Yeah, yeah.
Sir, how you are writing the node 3 equation? Can you?
Yes. Node 3 equation
Sir,
A3.
node 3. That is row 3. How you got the value?
Which value?
Row 3, column 2 in node
Node 3. The minus 0.4.
minus 0.4.
Yes. Minus 0.4 is A32, right? A32 is what? A32 is the negative of the conductance between node I and J. So A32
Yeah.
means between 3 and 2. Between 3 and 2, we have one conductance 0.4. So negative of that is minus 0.4 milli.
Oh, 2.5.
Then 2.5 kilo. This is resistance. Conductance is 1 by 2.5 K, which is 0.4 milli.
Okay. I confused with the
No, no,
voltage control current source.
no,
4
no.
milli.
Okay. Yeah.
Thank you.
Yeah. So, if there are no further questions, let me just quickly summarize. We have started with the circuit analysis basics, like how many independent sources are there in a circuit with anode and PV branches, and how many KCL equations we'll obtain which is n minus 1. Then we have started with the basic one, which is circuit with the resistor and current sources. We have initially solved for the nodal analysis at each node, and we got the expression in terms of matrix multiplication. And then we have seen that some shortcut is there using which we can directly write the matrix without even uh, writing any nodal analysis. Just looking at the circuit, we can write this expression, and using this, we can solve for the voltages. Now, we have solved a problem on the same, and we have seen that it is very simple. It is just two lines. We can directly look by looking at the circuit itself. We can write the expression, and only we have to do the matrix inversion to get this voltage expression. After that, we have seen if there is any current source at that particular node, the equation will change, but at other two nodes, the equation will remain same. So first we have written the equation at the other two nodes, and at the other third node, we have written Vx in terms of V1, V2, V3 and substituted and changed the expression a little bit. And then we got the matrix, and then we have solved for voltages. Even if it is current control current source, Ix will be substituted in terms of V1 and V2, and only at that node the expression will change. At the other two nodes, it will be the same according to that logic that we have learned. And at node 3, we have to just manipulate it, and then we have got the expression in terms of matrix multiplication, and we have solved for the voltages. Similarly, if there is any independent voltage source, you have to consider the super node. So first of all, with this voltage source, you will get one expression, and at that node where this voltage source is not connected, using the logic, we will get one equation. And by considering these two nodes as super node, we will get one equation. And you have to be very careful while writing this expression. That's why I have used two colors, so you will be careful while going through this video as well. So now using this super node, we got one equation. At node 1, we got another equation. Using this voltage source, we got another equation. So we got three equations, three unknowns, and we have written in terms of matrix. You be careful because two equations are in terms of amperes and one equation is in terms of voltage, because here these constant have a dimension Siemens and these constants are dimensionless. Even if it is dependent voltage source, from this voltage source we'll get one expression, and from the node 1 we'll get one expression, and from the super node we'll get another equation. And these three will lead to this matrix multiplication expression. And here also two of these equations have ampere as a dimension on the RHS and voltage on the RHS because of the dimensions on the LHS side. So now by solving this, we'll get the expression, and that's how we have solved. So do you have any queries today? There is less than a minute. This meeting will end. If you don't have any queries, then we can end this session. Any queries? Thanks, sir. So I hope this session is clear. I see only two people are interactive. Thanks for being interactive. But other people, if you face any issue, please go through this recording. It will be uploaded by tomorrow. And yeah, we'll see you in the next week. Thanks for joining, and good night. All the best for your assignments. With that, I will end this session. Thank you.